Very good morning to everyone. In this lecture, EC 8351 Electronics Circuits 1, Department of Electronics and Communication Engineering, third semester. In previous session, we are discussing the introduction of BGT configuration and what are the various biasing of the BGT configurations and also the stability factor of the BGT circuits. Now, today we are going to discuss about the compensation technique, that is a bias compensation techniques. What is a compensation techniques we are needed to BGT configurations? Here it is a temperature compensation and also the leakage current compensation. So these compensation technique we have to improve the stability factor of the BGT configurations. Now, first of all, the compensation technique it refer to the use of temperature sensitive devices such as a diode, transistor, thermistor, which provide the compensating voltage and current to maintain the Q point stable. For providing excellent bias and thermal stabilization bias, compensation technique is used. That is three different techniques. It is a diode compensation technique and a thermistor compensation technique and also the finally transistor compensation technique. Now let us move to the diode compensation technique. Here the diode in the emitter circuit diagram shows the voltage divider bias. With the bias compensation technique, here the separate supply voltage, that is VDD, is used to keep the diode in forward. If biased condition, if the diode used in the circuit of same material and type as a transistor, the voltage across the diode will have the same temperature coefficient as the base to emitter voltage VBE. So when the base emitter voltage changes by dou VBE with changes in temperature, so the diode voltage changes by diode voltage and dou VD and dou VBE. The changes tend to cancel each other. So now we applying the Kirchhoff's voltage law to the base circuit. So it is a stabilization of voltage divider bias mode in using the diode compensation technique. We have to use the diode in the emitter side. So now we have to feed back to the base and also the emitter side. So we get the threshold voltage, that is a VT is equal to base current into base resistance plus emitter base voltage plus base current into IC into RE minus diode voltage. So we have to simplify that the Kirchhoff's voltage law conditions, the IB into the RB plus RE plus IC into RE plus VBE minus VDD. So now let us move to we have to consider the leakage current. We have the collector current is equal to the base beta into IB plus 1 plus beta into ICO. The IB is equal to IC divided by beta plus 1 plus beta into ICO divided by beta. Substituting the value of the base current in the equation, the Vt is equal to Ic divided by beta plus 1 plus beta into ICO divided by beta into the resistance, that is the input and output resistance plus the output current into the emitter resistance plus the base emitter voltage minus the diode voltage. We have to simplify that equations. The collector current is equivalent to the amplification factor into the threshold voltage minus the supply voltage into input supply voltage in minus diode voltage. So here the resistance, that is the base resistance and also the emitter resistance into the current amplification factor of the leakage current. that is a leakage output current. So the whole divided by the input resistance plus the output, and the input and output both resistance of Rg, that is a 1 plus beta into Rg. So in this diode voltage is divider circuit, that is we have to see that diode is connected in series with the resistance of R2 in the voltage divider circuit and it forward bias conditions. The voltage divider bias, the emitter current is equivalent to the base voltage minus base emitter voltage into divided by Re is equivalent to the emitter voltage divided by emitter resistance. When we changes, that is when the base emitter voltage changes with the temperature, the output current also changes to cancel each changes in the collector current. The one diode is used in the circuit for compensation. The voltage at the base voltage is give as the base voltage is equal to the resistance of 2 voltage plus the diode voltage. Now we can consolidate the output current, that is a collector current is equal to the resistance of 2 voltage, that is a base resistance, and also the emitter resistance is there, plus the diode voltage minus the base emitter voltage divided by Re. These are the output current of the diode compensation technique. So we substituting this equation in the IC, we get the finalized output current in the technique. Now we can move to the changes cancel each other. So the collector current is given by IC is equal to VR2 divided by Re. So the change in base emitter voltage due to temperature are compensated by change in the diode voltage, which keep the IC stable at a Q point. Now we can move to the second compensation method, that is a thermistor compensation. This method of transistor compensation uses the temperature sensitive resistive elements. The thermistor, then diode or transistor, it has a negative temperature coefficient. Its resistance decreases exponentially with increasing the temperature. So we have to see that temperature we was the temperature resistance of a thermistor, that is a thermistor resistance. So the slope of the curve, the dou RT divided by dou T, with the increase of temperature the thermistor resistance decreases, hence the voltage drop across it also decreases. That is the base emitter voltage decreases with reduce the base current. This will offset the increase in the collector current with the temperature. The IC is equal to beta IB plus 1 plus beta ICO. So this equation shows there is an increase in ICO and a decrease in IB. It keep in IC almost constant. So the thermistor is connected between the emitter and the VCC to minimize the increase in collector current due to the changes in the ICO and VBE or beta with the temperature. We can see the IC increases with the temperature and the thermistor resistance decreases with increase in temperature. Therefore, the current flowing through the emitter resistance increases, which increase the voltage drop across it. Now the emitter and base junction is forward bias but due to increase the voltage drop across the emitter resistance, the emitter is made more positive with reduce the forward bias voltage of base emitter voltage. So the bias current is reduced. That is the condition of this thermistor compensation technique. Now we can move to the sensistor compensation. Here the R1 is replaced by sensistor, that is the resistance of R1 is replaced by using the sensistor. Now the thermistor resistance and R2 resistance of potential divider. So as the temperature increases, the sensistor resistance increases, which decrease the current flowing through. Hence the current through the R2 decreases with the reduce the voltage drop acrossing it. The voltage drop across the R2 is the voltage between the base and ground. So the base emitter voltage reduced with decreasing the 16. It means when the collector leakage current, that is a collector base leakage current, increases with increase in temperature, and base current reduced due to the reduction in base emitter voltage, it maintaining the IC is fairly constant. That is a transistor compensation technique of BJT. Thank you for watching this video.